All right, well, welcome back to videotaping. I had a problem with the home internet, so they're going to come by and fix it on Monday. So I ran over here to the university, stuck in to my office in a classroom so I could make you guys this video. So let's come over here. This is your homework number 6 helpful hints video that I try to help you out since we can't have office hours on campus and you guys can't come by and see me or anything. So hopefully these have been helpful. Let's take a look at this first problem here that you have on your homework. It says this: let R and S be commutative rings, and let sigma go from R to S be a homomorphism. So we got ourselves a ring homomorphism from commutative ring R and commutative ring S. Prove that if sigma is 1 to 1 and B element of R is actually a zero divisor, then sigma B is a zero divisor of S. So if B element of R is a zero divisor of R, then sigma B will be a zero divisor of S. Now again, in this proof, what you're really actually proving to me is that homomorphisms are that property preserving concept. So when you start mapping some of these special properties, they're going to map over from one ring to the next ring. So first thing you got to do, obviously with this guy, is you got to talk about all the things that you're given. So what are you actually given in this particular problem? Again, this is my scrap sheet of paper, so this is not the way I'm actually going to write it up or anything like that, but it shouldn't be that big of a proof because only you have to do that much room. So we're given, first off, sigma going from R to S is a ring homomorphism, and R and S are, I'll abbreviate, commutative rings. All right, we're also given that sigma is injective. That's the word you really should use, 1 to 1, just to help you guys out with that. And I'm also given that B element of R is a zero divisor. So let's talk about each one of these guys. So I've got my classic ring homomorphism. So I have famous theorem, I got definition of homomorphism. I also got theorem 3.10 to be able to help me out with this stuff. I've got sigma being injective, 1 to 1. That means this, that one element in R, so if you got one element in R, and will map to exactly one element in S. And remember, because we have ring homomorphisms, you know that sigma of 0R is the zero element in R, would have to be equal to 0 in S. That is actually theorem 3.10. 1 maps to 1. You know, for any case, and for this 1 to 1, so if you've got little r element of big R, there exists a little s element of big S such that sigma of R is actually equal to sigma of S, and this is a unique element. For any element R, there exists, and I put the word unique S in S, such that sigma of R is equal to S. So I've got that 1 to 1 thing going for me. Definition. The big one is I got B element of R is a zero divisor. Let's talk about your definition of zero divisor. Your definition of zero divisor is very straightforward. That means that B is not equal to 0 in R. First off, B is element of R. B is not equal to 0R, and there exists, pick your favorite letter, we'll call him A, element of R, such that A is not equal to 0 in R, but zero divisor. A times B does equal 0 in R. It's two non-zero elements multiplied together to give me 0. That's the definition of a zero divisor. But you do have to talk about this idea of it's non-zero element, a traditional zero divisor. Now, let's talk about what you want to show. So put it down here. Want to show. I want to show that sigma B is a zero divisor of S. Well, how do you show somebody is a zero divisor? That means, what do I have to show? That sigma b is not equal to 0s. That's important. And there exists some element, we'll call him u for right now, in S, with u not equal to 0 in S, but u times sigma b will equal 0 in S. So this is really what I want to show right here. Okay? Now I got to figure out who this u is actually going to be. Now, let's talk about all the things we got over here. We also have a mapping. So once I set up this situation here, again, you've got to write them up and write them up properly by stating all your givens. And so once I got the a times b equals 0r, I would apply sigma to both sides. Now, you remember sigma is a function, not an actual number you're going to distribute. That's what you said. You're going to apply sigma to both sides, and you end up getting sigma of a times b is equal to sigma of 0r. Now, that's what you need to play the game on. We know that sigma of a times b will be equal to sigma a times sigma b. What's my reasoning behind that? That is actually the definition of homomorphism. So you'll notice in chapter 3 and 4 in particular, we're very heavy into the definitions. This is the old definition of homomorphism. Okay? And so we also know that sigma 0r is equal to 0s. We talked about him being part of that theorem 3.10. So when you substitute, you sub in, you get sigma of a times sigma b, and for that guy is equal to 0s. You get your equation. Now the big question is, all right, so you got your equation. I think we know who we're going to be multiplying by sigma b to get that 0. But why is sigma of a non-zero? Well, it goes back to this injective idea. 1 to 1. Who automatically maps to 0s? 0r does. So, since 0r maps to 0s, sigma of a cannot map to 0s under the guidelines of being injective, 1 to 1. So that's why it's not going to be 0. So this is not 0. Same reasoning for this guy. Sigma b is not going to be 0 because you already know who maps to 0s. So sigma b cannot map to 0s. And because b was not equal to 0r. And therefore, you've got all your definitions. Now, I've wrote this up in kind of a discussion format. This is clearly not the proof. You get nothing for writing it up like this. I'd actually take off extra points because this is just kind of thoughts being written down. This is your want to show page type thing here. You go back, start with your definitions, write in paragraph form, do your substitutions, and make sure that you hit all your points that you're trying to make about applying sigma to both sides. Don't multiply by sigma on both sides. Sigma is a mapping, so it's a function. So you take what you do to one side, you do the other, and you're going to take sigma on both sides. Look at number 2 here. Once again, we have a commutative ring where R, S, T are elements in ring R, and where R is not equal to 0 in R. Prove that if SR equals RT, then either S equals T or R is a zero divisor. Now on this particular problem here, you've got yourself a commutative ring, so order doesn't matter. Once again, it's just like we had in this last problem up here. Okay, so the problem is this word right here in terms of your proof, the word either. How do you show either this or this? You got to put it in cases, case 1 or case 2. Okay, so basically you're going to work with your definitions here. Now when we're talking about zero divisors, what I'm talking about here is R being a zero divisor. I'm going to multiply R, which is non-zero, by another non-zero element, and I got to get 0. Well, if you've got an equation here, that's what you need to start with. RS equals RT. But if you're going for zero divisors, you always set stuff equal to 0. So I'm going to subtract RT from both sides. So I get SR minus RT equals 0 on R. But remember, if I'm going to do any kind of factoring, they got to be on the same side. But luckily, I have a commutative ring. So by commutativity, SR minus TR would be equal to 0 in R. And then you can factor out your R. S minus T times R equals 0R. And again, statement reasoning here. So this is pretty much given. This is by subtracting RT from both sides. This is by commutativity. This is by the distributive property. Make sure you use your big words. It's also known as factoring. I would accept that. So now, let's talk about this stuff. And this is what I'm talking about your cases here. You got case 1. Now R is given to be non-zero. So you got to talk about S minus T. So S minus T has got one of two things. If two guys multiply together equals 0, either a guy is equal to 0 or, case 2 here, he's not equal to 0. Now, you can't argue logic here. You're either 0 or you're not. If this guy is equal to 0, then one of your cases will be satisfied. If this guy is not equal to 0, and since R was not equal to 0, use some definitional properties and state what's going on here. So the trick is, honestly, knowing your definition. So both problems number 1 and problem number 2 were really big in understanding and elaborating on the concepts of the definition. Now again, you've got to write this thing up in paragraph form and statement reasoning within your manipulation of the equations, using mostly on these two problems is definitions. And of course up here we did kind of throw in a theorem 3.10, and of course a definition of a homomorphism and the definition of a zero divisor being thrown at us. But yes, you need to know this stuff. So that's going to be very helpful on your next coming test. So on this problem right here, this is a very similar problem that you've seen before. However, we got polynomials instead. So it's very similar. You know, I told you this is what I was going to be doing with you guys. Once we got into the polynomial rings, they work like integers, but they're polynomials. So what are you given here? You start off with the givens. You're given two guys. You're given the GCD of AX times BX and AX CX is equal to E of X. And you're given that the GCD of B of X and C of X is equal to D of X. Okay? So, got down here our want to show, WTS. What do we want to show here? We want to show that E of X, I can use symbols on my scrap paper here, divides A of X times D of X. Now you write that on a test, well, you'll like 50 points off just because at this level of the course. You got a writing intensive class here. So E of X divides A of X times D of X. What does that mean? By definition, divides. Remember, nobody's an integer in this world. Everybody's a polynomial. What we really want to show is A of X times D of X is equal to E of X times some polynomial. That's what I'm going after. I'm going after an equation of A of X times D of X. Now, remember with your GCDs, you got two options. You got the definition of GCD, which gives you a little bit of equations, and you got the theorem 4.8, equivalent to that theorem 1.2, but quote them correctly with polynomials, it's theorem 4.8, which means there exists a polynomial U of X and V of X, element of F adjoint X, such that, you know, your polynomial times U of X plus the other polynomial times V of X equals the GCD guy. You can write a big equation out of this guy. So typically when you get two GCDs, you want to use the definition on one and you want to use the theorem 4.8 on the other. Well, since I want an equation with A of X times D of X, I want a big equation. This is the dude that I'm thinking that I should use theorem 4.8. So there exists U of X and V of X polynomials and F adjoint X, such that you get this equation, B of X times U of X plus C of X times V of X is equal to D of X. With this guy here, because I don't need something equal to E of X. There's nothing I'm trying to prove equal to E of X. I want to factor an E of X out. So this is your strategy when it comes to, like, for example, tests and final exams. You want to kind of plug in for that E of X. That's when you're going to use the definition of GCD. Also equivalent in this particular section, you could use, I think it's called corollary 4.9 on this particular stuff, but definition of GCD will work, which means that definition of GCD is that E of x divides A of x times B of x, and E of x divides A of x times C of x. But to get that equation out of it, then you got to use by definition of divides. Pick some letters. You know, A of x times B of x would be equal to E of x times, let's see here, W of x. I haven't used W in a while. And the other one is A of x times C of x is equal to E of x times Z of x, where W of x and Z of x are elements of f adjoint x. Now, of course, I'm going to write this up properly, but this is the definition of GCD, which I got to use the definition of divides to get myself some equations. So here we go. But remember, what you're trying to show here is that E of x divides A of x times D of x. So I need an equation with A of x times D of x. Well, I've got the D of x part. So the trick is, well, multiply what you need to. But what I do to one side, I do to the other. So by multiplying by both sides, I'll get the A of x times B of x times U of x plus A of x times C of x times V of x is equal to A of x times D of x. So I took this equation and I multiplied by A of x on both sides. Okay, I'm trying to get you the strategy because I don't want to do the entire thing for you. But now I got to get those e's in there. So A times B gets replaced with E times W. A times C is going to get replaced with E times Z. And then you can factor out your E. And then you figure it out. Once you factored out the distributive property, you figured out who the polynomial is going to be. And remember, just like when it comes to integers, when it comes to rings, sums and products of elements of rings are as an element of ring. Sums and products of polynomials is a polynomial. You've got to tell me who the polynomial is. Therefore, by definition, of divides, we win the game. So again, I'm giving you hints and strategies on this thing, but I'm not writing it up for you guys. I want you guys to take the hints here and actually go write it up properly. Look back at how we wrote it up. And this is a very similar problem. Those videos are still up there. You can go back to some old videos from chapters 1 and 2 and look how we worded that. But now we got polynomials, so it'll be done very similarly. This one is another one that's very similar. And that is that you were given f's a field and everybody's a polynomial and f adjoint x. You're given a GCD and you're given both f and g divide h. What do you want to show? You want to show that f of x times g of x divides h of x times d of x. Which means by definition of divides, you want to show h of x times d of x is actually equal to f of x times g of x, once again, times some polynomial, and I got to go figure out who that polynomial is going to be. So how do I go about doing that? Well, again, you're given that d of x is equal to the GCD of f of x and g of x. Well, I'm trying to show that, once again, f times g divides h of x times d of x here. So I want an equation with h of x times d of x. Well, I got two options here. I got definition of GCD and I got theorem 4.8. Well, since I got the d of x, I need a big equation so I can factor out f times g. So I need a big equation. When you need big equations, you want to use your theorem with polynomials 4.8. So by theorem 4.8, there exists polynomials u of x and v of x, elements of f adjoint x, such that f of x times u of x plus g of x times v of x is equal to d of x. But you're also given that both f of x and g of x divide h of x. This is by definition of divides, and remember your wording. Declare them before you use them. There exists polynomials. What do you want to call these guys? Just to throw you guys completely off, alpha of x and beta of x, elements of f adjoint x, such that, okay, now f divides h and g divides h. H is going to be bigger, so I'm going to write them up here. H of x would be equal to f of x times alpha of x, and h of x would be equal to g of x times beta of x. Just going the little Greek letters at you. So these will be my substitution guys, okay? So, what do you got here? Here is my equation. I need it to be times h of x. So, start with the classic. So as you have this f of x times u of x plus g of x times v of x is equal to d of x. Then you're going to multiply both sides by h of x. That gives you h of x, I'm going to go ahead and distribute, times f of x times u of x plus h of x times g of x times v of x is equal to h of x times d of x. Now remember, on your actual proof, you don't get to skip steps. You got to tell me by multiplying by h of x on both sides, you got h of x times this is equal to h of x times d of x. By distribution, you end up getting this. So I'm skipping some steps here because that's your job to catch the steps in between this stuff. But now here's the real trick. I want to be able to factor out f times g. This guy's got the f, it needs the g. So you got to plug in the right guy in here. So I would plug in this guy, substitute him in. This one's got the h of x and it's got the g already. So this one needs the f. The f is this guy up here. So I'll plug him by substitution. I'll substitute these two guys in appropriately. If you substitute them in the wrong spot, you won't be able to factor anybody out. You get a bunch of f of x squareds and g of x squareds. You don't want that. And then you can factor it out, and you end up getting the f of x times g of x, and the stuff that's left over will be your some polynomial. And remember how we actually write this stuff up. Since all the parts, u of x, v of x, and all the other letters are polynomials in f adjoint x, then this sum and product is going to be a polynomial in f adjoint x, because f adjoint x is an integral domain. It's a ring, but it's actually an integral domain. A field adjoined in x, polynomial rings, when the coefficients come from fields, make integral domains. But integral domains are rings, and therefore they have the closure property. So this guy is going to be an element of f adjoint x, so thereby definition of divides, therefore we win the game. So there we go. The last one on this one was a little bit longer homework for you guys to actually attempt, and that is we want to write this particular polynomial as a product of irreducible polynomials. Now, and I gave you this finite field adjoint x. So if you watched my awesome last video on sections 4.3 and 4.4, I talked about this idea, and it goes back to high school from the remainder theorem and the factor theorem. So all my educators that are in my class right now are very excited because that ties back into something they teach all the time when it comes with polynomials, because with polynomials you analyze roots, zeros, x-intercepts. And when you got a finite field on this guy, what you're going to do here is you got z5 adjoined x. So if this function, this polynomial, 2x to the fourth plus 3x squared plus 4x plus 1, if it's ever going to be equal to 0, you basically it's going to have to find the zeros here, but your coefficients come from z5. So the x's are going to be either 0, 1, 2, 3, and 4. Okay? And you're going to do f of x, and you just literally, I use my calculator. You saw me on the video. I plug it into my calculator, and I'm going to get some numbers. But then I'm going to have to convert them back to that z5 numbers, and which ones are going to be 0 will end up being my roots. And so my roots, my zeros, I'm going to take whatever numbers they are, and I'm going to do synthetic division on this guy, and I have to convert him back. So I've got the coefficients of 2, there is no cube term, remember that. There's a hint for you on the test. 3, 4, and 1. This is constant x, x squared. There is no x cubed, and there's your x to the fourth. You put your constant, whatever number you found to be your 0 here, is 0, 1, 2, 3, or 4. You skip a line, draw a line, and do your synthetic division from high school. So you bring down your 2, you multiply and you add, and eventually you're going to get some kind of number over here on the last block, which is your remainder. Don't forget, you've got to convert them back into the world you live in, which is your z5 adjoint x, and this block should be 0 if it's a true 0 over here because of the remainder theorem. And this gives you what it factors to. Okay, so and if this is c, then f of x would be equal to x minus c times, and you have to convert this back to your polynomial, but you're not done yet. You have to worry about double roots. So if you had another 0, you would continue to divide on it, and you get x minus c, x1, x minus c2, and then the resultant here. And then you got to go back and double check, make sure this thing wasn't a double root. So you got to do synthetic division on the numbers again, or you can plug them into your function to see if you're going to get a 0 again. If you get a 0 for the function again, you got to synthetically divide it out. And don't forget, you can't have an x minus. This is supposed to be in z5 adjoint x. So all the coefficients have to be pluses, and they got to be 0, 1, 2, 3, 4. Now typically we don't put the pointy brackets on the polynomial ring, but you do have to put, if this was x minus, for example, 4, then the equivalence would be to convert them into z5. Minus 4, you add 5 in z5, that would be x plus 1. So you would write him as x plus 1 times these numbers here after you convert it to z5. So again, watch the last section, the section 4.4 video in particular, and take a look at that thing, and then write it as a product of irreducibles. Now, the last thing is, if you factored out your constant, honestly, factoring out constants in real math is not real factoring. Okay, you factor out a constant because a constant is a unit, and f adjoint x, a field being z5, and 5's prime, so this is a field. We talked about being associates. So factoring out a constant is not real factoring. To factor, you got to knock them down by a degree. So if you're a little confused on what I just talked about, please go watch, because I did a couple of these wonderful problems for you guys on section 4.4 video and stuff. Hope this has been helpful. And so I did push the homework due date back to 11 o'clock because I had some internet issues at the house, so I had to sneak in here to campus to make your video for you. So it got a little bit later than I wanted to release it out, so I'm going to buy you some more time that way. So study hard, and I'll see you on the next video.